So we've seen blurs in all shapes and forms. We know the box blur, we know the blur HQ, we know the anisotropic blur, we know the directional blur, we know blurs all over the place. But today we're going to have a look in how to create your own custom blur inside the pixel processor of Substance Designer. Not specifically to have another blur node that is more cheap or more performant, but actually just to show another way of doing a blur and specifically teaching how to create this specific workflow inside Designer, inside Pixel Processor to show you how to get a bit more technical. So first things first, this blur that we're going to build here is not going to be any more performant than the natural blurs that you have inside Substance Designer. The reason for that is, if you let me quickly display the timings here, that this stuff, like these native nodes, those are built like in code already. Like these are offline texture. There's nothing that we need to image process here. It's actually code based somewhere native inside the depths of Substance Designer. So if we actually want to have like a more performant blur version, this is most likely not going to work. By the way, the blur HQ color is not a native node as the blur. You can see it by the color here, like this beige color indicates that it's like an atomic level node. So this color is basically built of different directional blurs that are like mixed into each other. And we're going to build like the same blur like this, which is again not going to be any performant, but it's just to show you how you could technically create your own blur version. So let's jump into it by creating a pixel processor. And as usual, I'm going to switch the output format to 32-bit just to be sure that whenever we are clipping out of range, we can debug this and it works correctly. Let's plug this in here. We can stay at color and we start editing the function. So the question is, how does a blur work? Actually, a blur is basically using, so let me quickly create a screenshot here and we can like draw over this in a second. So let's say we have like a pixel here, right? So to blur it, we need to like sample pixels in, for example, x direction, positive x direction to the right, to the left, up and above, like maybe in the directional. We need then add them all together, which will create like some value which is basically higher than 1. Then we're going to multiply this by a weight. So these samples, these fetches here, they can all have a different weight if you want to. A classic box blur would just go with a weight of 1 for wherever you're blurring. A Gaussian blur, for example, could have a weight in the center of, let's say, 5 and like 2. Well, these are good to use 2 at the outer bounds and like 1 on the corners, which would create like a different type of blur because we're giving the center one much more presence and much more accumulation in the later weight. So yeah, so we are sampling from our initial pixels to a certain direction, multiplying this with a weight, which is going to be 1 in this example, just to facilitate things a bit. And then we're going to like divide that new color that we accumulated by the number of samples that we used to create this. So in a, let's say in a 3x3 kernel, which would be like this. So we have the center pixel here. Wait, where's my color? We have the center pixel here, which is going to be 1 sample. And then we have like 1, 2, 3, 4, 5, 6, 7, 8, 9 in total difference. So we had to like divide this by 9, which would be the total number of samples we used to blur that specific part here. Of course, if we are doing this like 1 time for the whole image, we're not going to see much of a difference because this is a very small kernel, you could say, because we're only sampling like the direct neighbor pixel. So we're going to not see a difference at all. So we would have to do this like on a bigger radius, on a bigger sampling size, and a few times. So what we're going to build is we have that center pixel, and then we have something that we call R, or radius. And this defines how far to the left and to the right we're going. So for example, if you're having a radius of 30, we're going like -30 and +30 in each direction, which is again the number of pixels we're going to use to sample and then divide by. But this is going to be making much more sense when we continue. So first of all, we need our position coordinates, because this is like this is basically our UV. So this is telling the sample color where to sample the color from. So we are sampling at all UVs at all positions, which is basically our input image. So the next thing we need to do is think about creating a loop, because we need to repeat the sampling as often as our radius indicates. So in order to do that, we first of all need a few things to set up. So I will briefly explain how to create a loop here, but also be sure that you understand the principle of how to make this node-based. So first of all, we're going to create a float for. Set the alpha to 1, just to be sure. And we're going to set this. So this is setting a variable, and we're going to call this accum color, which is going to be the accumulated color later on. Move this up here. And we need a few more things. First of all, we need an integer, which is going to be our radius. We're going to cast this to a float to make things a little easier down the road, because intermediate values for this radius is not going to work, because we cannot sample like 0.25 between pixels. So each step should be like a full neighbor offset. So working with integers is much more easier. We're also going to set this to a variable called radius, or r. And then we need another variable, which is going to take count of how many iterations we went through already. So we're going to repeat this loop as much as we have steps to fulfill, and the radius is in positive and in negative. So we need to grab this radius. Oh, by the way, let's link this all in sequence nodes, because we want to pass all this information down into our while loop, which I'm going to create here. And this has this like init drop here, or this initiation. And this is basically asking for what kind of data do I want to have before I execute the loop. And we can pass all this data by linking them into sequence nodes and then plugging them in here. Right, so now that we have like created that variable here and passed it through the sequence node down to this one, we can now grab it here. And we are going to negate that. So instead of like, let's say we are starting with 20 samples. Oh, that's 200. Let's say 20. Yeah, we are going to grab those 20 and we're going to negate them. So it's now -20. And now we're going to set this to I, which is basically going to be our iteration number. And it's going to start at -20, because we're going to start at the most, wait, this is left for you. We're going to start at the most left pixel and going through all those one until we had 20. Right. Now we need one more thing, which is going to be the actual size of the step that we're taking. So right now we're dealing with full numbers like 1, 2, 3, 4, 5. But in coordinate space, this would be like jumping through the whole image. So this goes from 0 to 1. So adding 1 up would be like going the full image size. So we need to know how big actually 1 pixel is. And to do that, we can use a simple trick, which is taking a float 2. We need this because we need to divide 1 by the size. So the size will hold in X and Y the size of our input, which we can read down here. So it's 124, 124. And if you divide that, we get the size of like 1 pixel, basically. Yeah, and since this is quadratic, we only need to like get X or Y. It doesn't matter too much which one you take. And then we have to set this to pixel size. So 1 pixel would be the fractional part of this size to 1 pixel. And we also have to pass this down in the sequence node. So this is everything as like outer data we need to make this work. And now we need an exit condition. So how long should this loop run? And this loop run, this loop should run as much as we have samples in the radius. So we need to get I, we need to get I, and we need to get radius. And we need to say that as long as radius is not and we need to say, or we can say that if radius is lower than I, then exit this condition. And remember that we set radius to be 20 and we set I initially to be minus 20. So right now I is 41 actually, we're going to get to that. 41 units smaller than radius, so this loop is going to be executed. Also make sure to double click your loop node and set the max iterations to -1. So the loop is now determined by how many iterations we are basically setting up as logic inside the exit condition. We can also limit that, but again, that's not very dynamic because we want to treat our blur like the other ones with the slider, like how strong is that blur going to be. All right, so now to the actual logic. We sampled the image here at our position, but now we need to make sure that we sample the image at like one of these fractional parts, one of these neighbor pixels. So to do that, we first of all have to get our float I. By the way, this is everything that's going to happen in the loop, in the body. So first of all, we're going to grab y, which initially is going to be -20. And then we're going to multiply this by our texel size because we want to go only so much steps and size ahead, which is going to be this. Now we have to combine this, and this is a little bit different to usual blurs, but this blur here, as you can see in the name up here, is called a separable blur. So we are basically dividing the blur into horizontal blur and vertical blur. And each one of these pixel processors is going to take care of one of that. So right now we are only thinking about one dimension to blur, similar to what a directional blur would do. Yeah, to see the final result, we basically want to get here because we're only blurring on the vertical axis right now. And to make sure that this is happening, we need to combine it to a vector float 2 because we're going to add this offset that we're calculating here. So our iteration time, or the neighbor that we're picking, its size, and this is going to be added on top of our position. Yeah, and so that we only sample into the x direction, we need to set the y to 0 here. And this is going to allow us to offset this position value now by -20 pixels to the left. And in the next iteration, when I is becoming -19 and -80 and so on, we're basically, let me quickly grab a screenshot again to paint this in here. So let's say this is our center pixel, and this here is -20 from I. Then we're multiplying this by texel size to make sure that we have exactly 1 pixel in size. And this whole loop is running once, and it's spitting out a color for us. We're going to get there. And then in the next loop, we're going to sample this one here, which is at -19, and so on, until we hit the center pixel, which is our position, right? So position is 0 in this case. And then again, this is going to be repeating along +20 until our loop is finished. Right, so now we need to sample at that position, and you're going to see not a lot of a change. So yeah, there's no change happening here, and this is totally expectable, by the way, because right now this is happening outside of our whole sequence stuff here. So if I output this now, actually we should see a difference, I think. Let me see. Not sure. No, we are not seeing a difference. Okay, but that's not of an issue. It maybe has to do with the logic here. I don't pay too much attention when it should work. I only try to track down issues once I have the loop set up. All right. So now we are knowing at which pixel we need to sample the color or our input image. Let's zoom out a little bit. And now we need to grab our accumulated color, which we initialize to be 0. And we are adding our sample onto the accumulated color. So in the first pass, we are sampling at -20, the neighbor. And this is going to be added on top of accumulated. So in the first pass, we are like feeding just our input image at that sample into accumulated color. And then again, when that is done, we need to feed this back into the same variable, because doing this will override what we did in the sequence pass up here for one iteration. And in the next iteration, we're going to grab the sample from the loop before, which is now into written into accumulate color, and we're sampling at -90, and now we are adding -90 on -20 and setting this again. So we basically keep track of the accumulation from before. All right, and we can do this and output, but again, it's not going to do anything because right now we are not incrementing I. So I is never changing. We're only sampling once, or basically we are sampling indefinitely at the same position because nothing is happening. So what we need to do is create another sequence now down here. And we're also going to need to grab I, which is our like increment, our index, so to say. And then we need to add 1 to it. And again, this is happening all within one single iteration. So we are grabbing I, which is -20 right now. We're doing all this. And then we're incrementing I by 1. And we're doing that the same way. We get that variable from up here. We add 1 to it and we set it again. And this will be passed with the sequence like this. Also, make sure only what is down in the sequence, not so the lower pin, is going to actually carry data over to C or evaluate, and whatever is like put in the upper pin is only like passed along the sequence. Okay. So if I would do this vice versa and plug it in here, we would see the output of Y, and if I do it like this, we will see the output of accumulated color. All right, so what happened here? Now everything got like very bright yellow, and when we are inspecting the values, we can see that we are overshooting by quite a lot. And this is expected to happen because we yet only accumulated all those samples and added them together, but we never divided by the final weight that we accumulated. So the weight is basically identical to how many samples we actually used to get there. And we know exactly how many samples we have here. So we can get radius again. And we know that radius is going from negative to positive. So -20 to 20, or basically that range and negate it. So we can multiply this by 2 because we know we have like the positive and the negative values. And then we also need to add 1 to that because doing this calculation doesn't respect the center pixel, which is at 0. So we have to add 1 to it. And this is, by the way, the complexity of that certain logic, that certain blur that we're building. So it's only going to iterate as much times. Like radius times 2 plus 1. This is how much iterations it's going to run through. So if we increase the radius, we are also increasing the calculation time of this loop naturally. And the lower it is, the lower is going to be the calculation time. Right. Now we can take a scalar division flow too, because what is happening here? Yeah, because we need to divide this float 4 by our summed weight. And if we output this now, we're going to see our correct colors again, and you're going to see the blur. And if I now increase this number here, you're going to see that we basically recreated the same that the directional blur did. Let's see if we can, yeah, we can hit about the same range here. Okay, so with one pixel processor, we built a directional blur, which is cool. But again, we're only sampling in one direction. The good thing about separable blur or blur logic is that it can run independently in axes and then be accumulated again. So without having the need of doing some crazy math in between here or account for like several directions of all those samples, we can just sample along one axis for the whole image and then do the same based on this blurred image in the vertical axis. So all we have to do right now is to duplicate this pixel processor and plug our image from before in here. And then we have to change like one simple thing, and that is here when we are building that vector flow 2 that is essentially telling us from where to sample that neighbor from. We're going to swap these two, so now we are going 0 in x but so and so much in y, and you can see that the final output now much more looks like a traditional box blur. And you can see that now the timings just rose up tremendously, because it's just not as performant as do it by code. But you can see that if you're comparing these are basically very similar. I think it's only a matter of the actual radius intensity. So if I lower this a bit, yeah, they're starting to feel like the very same. Great. So one final thing would be to expose this radius. Wait, here, this radius. So this number should actually be exposed outside if you want to have like a controllable blur. Also because if you now independently tweak these numbers here, which, yeah, if you now independently tweak these numbers here, you're going to have like some kind of non-uniform blur. Like it's only in two directions, but you can blur more in one direction than the other. And in most cases, you probably don't want that. But again, I wouldn't recommend using this node anyway, because it's not comparable in timings with classic blur operations. Like it's just not. But it's a cool way to do another type of blur. And there's like much more how you can, like much more ways how you could achieve that. But just to show you one example of how to execute that within the pixel processor.